So we're going to talk about what zero-knowledge proofs are, what you can use them for, and what are the limitations, and just to give you some sense on how, like what's different to normal programming in blockchains. Okay, oh, it works, nice. Yeah, so what they are, what are the use cases, what are the limitations. So let's start with the basics. Zero-knowledge proofs is probably a bad term. They should rather have been called something like proofs of honest computation, because what we really do is we prove this is a family of cryptographic protocols which allows you to convince a counterparty that you have performed some computation correctly on partially private data, partially public data, and on some predicate, some publicly known function, which we both know. To understand this better, let's take an example. You can prove to somebody that you have a pre-image to a certain hash. Now, the protocols will allow you to do this. The hash function, like SHA-256, will be our predicate. The pre-image will be your secret data, and the hash will be the public data. So you present somebody the public data, the hash, and then you either prove that you know the pre-image, or you prove that you can revert engineer the hash function, which is very unlikely. So like most likely that you actually know the pre-image. And the computation which you prove can be fairly complex. It has some peculiarities compared to normal computation. It's not a von Neumann architecture, but you can do anything as complex as proving that you performed the entire blockchain state transition correctly. So if you look at this function, we take the cryptographic commitment of the old blockchain state, represented, let's say, by a Merkle tree. So you take the old Merkle tree root, you make it public, you make a new Merkle tree root public, and you display the details of the transactions, maybe. And then the path to this Merkle, to the Merkle proof updates, and the signatures which you collected from users, you keep private, but you can still prove that you performed the transition from previous state to the new state by applying all the transactions correctly. That you verified the signature for each transaction, that you subtracted the amount which you're sending from the from account, added it to the to account, updated the nonsense correctly, and maybe perform some other contractual logic which is in the state. So there are different protocols which you can use for zero-knowledge proofs. You might be familiar with them. This is not a complete list, but I want to argue that in blockchains, we're only or mostly interested in zero-knowledge proofs which are succinct, such as Starks and Snarks, where S stands for succinctness. What does it mean? It means that the verifier, which is an algorithm which checks the proof and makes sure that it's actually it's correct and you made the computations correctly, is strictly less in computational complexity than the amount of steps of your computation. And same applies to the communicational complexity, in other terms, to the proof size. The proof size also must be much shorter than the amount of witness for the original proof generation. And why is that important? We replicate all Ethereum transactions to more like to tens of thousands of machines worldwide. And this is really important to ensure decentralization. Now, if you take computation and you make some piece of data, you process it somehow, you send it to everybody else, they have to do the same, exactly the same operations everywhere. Now, if you increase the amount of computational work you do, everybody has to increase. And eventually, you will reach the limits of the customary hardware, such as laptops and cell phones, which people use, and only big players will be able to verify blockchains, and this way we're going to lose the decentralization property. So this is not cool. What zero-knowledge proofs allow you to do is to have a lot more computations, which can scale, but the verifiers have to do still the same small amount of work. So the processing of the blockchain, the Ethereum transactions, the Ethereum nodes have to do very little work, but then you can increase it significantly. Of course, it has a cost. So you actually have to perform a lot more computations to generate these proofs, more than you would do to just compute the function itself. So to give you a sense of what it will cost you, if we have a very simple, let's say, layer 2 solution where you just make transfers and send some assets, single transaction, the proof of a single transaction will cost you about 4 seconds on a hardware comparable to MacBook Pro. And the breakdown will be something like this. So we measure the complexity of zero-knowledge proof programs. We call them circuits. And the complexity is measured in what we call constraints, which is a technical term, but they linearly correspond to the complexity. So you have most of the constraints go for hashes, which we need to check the Merkle proof inclusions. Some part goes for like complex hash functions. Not all hash functions are equally computable under zero-knowledge proofs conditions. And some very small amount of computational power goes for actual operations, such as updating the balances. OK, so yeah, so you have just different trade-offs. You have to take them into account when you construct your programs. But essentially, you can prove arbitrary computations. And this is really cool. And this technology is getting more mature. We'll talk about it a bit later. So yeah, we have, from succinct zero-knowledge proof families, we have 2 which are mostly known. We actually only have 2. Like everything else is not really succinct. The first family is called SNARKs, succinct non-interactive arguments of knowledge. They are fully succinct. So the verification actually only takes off 1. No matter how large your computation, verification will always be short and fast and cheap. And the proof size is going to be just 300 bytes, which is amazing. Right? You can compress the entire blockchain to just 300 bytes and use this as a proof. Starks have polylogarithmic complexity of verification and proof sizes. So the comparable Stark proof will be in order of 100 kilobytes, which if you use it for blockchains, it will consume almost entirely the gas limit of a block, which is not so cool. But they have an upside. They are post-quantum resistant, which may or may not be important, because if we have quantum computers, we're screwed anyway. But they don't require a trusted setup, which SNARKs require, because they are based on elliptic curve pairings. And the trusted setup is a nuisance. Like we need to conduct a ceremony with a lot of participants, and all of them promise to delete certain data which they used as an entropy as input for this setup procedure. And if at least one of them is honest, the entire procedure is OK. If all of them collude together, we have a problem, because they can fake proofs. So if we have to do it just once, it's going to be OK. The older version of SNARKs were requiring you to build a trusted setup for every application, which is probably very difficult logistically and politically. So we have a newer, sorry, it's not working again. Nice. We have research going on in this direction with a lot of brain power involved, which gave us Sonic and proof systems which will probably appear soon, which is similar to Sonic, which require a trusted setup to be done only once, which can be reused for any application. So you as developers will not have to bother about it. You can just take the one which was produced by a large body of highly prominent participants, maybe Ethereum Foundation, maybe other blockchains, maybe some other organizations, and you can reuse it for your dApps without bothering about security of this. And if you don't trust this consortium which produced the trusted setup, you can always add your entropy on top, and then you can be 100% sure that there was no compromise. So this is the updatable property. So we are pretty confident that the Sonics are currently less efficient than Groth16 than the previous generation of SNARKs, but work is being done to make them more efficient. And very soon, it will be possible to use them for blockchains for very broad variety of applications. So just keep an eye on it. And let's talk about the exact use cases. So we have these 2 properties, zero knowledge, which allows you to hide at least part of the inputs of your computation, and succinctness. And they can be translated into privacy and scaling correspondingly. So let's talk about privacy. The most obvious use case for privacy is anonymous and confidential payments or transactions or mixers. Like you can transact with other people economically without disclosing this to the entire world, what we have currently on blockchains. And anonymous means that you hide the recipients and senders. Confidential is a slightly different property, you just hide the amounts. You can have both properties or just one of them. Maybe it's going to be difficult from a regulational standpoint to defend anonymity. Maybe confidentiality is easier, or maybe we need both. It's going to be up to you to decide what you want to use for your Dapp. Then we can just use zero-knowledge proofs for partial data disclosure, which opens a row of very interesting possibilities. You can, for example, disclose your bank account information without, you can make statements about your assets without disclosing them. And you can say that I have enough solvency, but I'm not going to tell you how much exactly is in my account. Then you can use it to construct KYC checks, where you can prove to the authorities that your users have done KYC, but you're not going to tell them who these users are. You just make sure that they are on the white list or that they are not on the black list, which is really interesting. And finally, you can do things like voting or like anything else where in voting, for example, you would say that all users have voted only once, but you're not going to disclose what the inputs of the vote, what the votes actually were, right? You can make it private. Finally, we are going towards being able to construct smart contracts which are very generic, which operate on partially private and partially public data, and this will give you ultimate power to create any applications which you want. And I just want to remind you that current families of zero-knowledge proofs allow you basically arbitrary computation. It's just going to be bounded in size, but you can do anything, any program. And it's going to be very easy to do. We're getting better tooling, better languages, better frameworks, and profiling tools, and so on. Now, scaling is super important because we all remember what happens when blockchains run out of capacity. If you want your Dapp to be successful, then you probably expect a lot of users at some point of time in the future, and you want to be prepared for this. So you want to plan ahead of how you're going to handle the scaling situation when it occurs. And we have many different approaches on layer 1, on layer 2. Most of them are making certain trade-offs in the blockchain trilemma. Right? So they either sacrifice the decentralization and make centralized or consortium, like reduce decentralization of the services, or they make certain trade-offs on the security, or they make users to do really hard work, and it's going to be not very usable. Zero-knowledge proofs allow us to circumvent a lot of these limitations and have systems that behave almost like layer 1 blockchains. So they maintain the security properties of layer 1s. If you put your money there, they're going to be as safe as though they are on layer 1 without you having to do anything. Now, they keep your systems decentralized. You can have multiple operators and keep it such that censorship resistance is ensured. And yeah, scalability is going to be achieved through the succinct property of zero-knowledge proofs. On the computational side, at least, on the data side, we can reduce the data which needs to be propagated through the network a lot, because we can omit parts of the data which are discarded after the transactions are processed. For example, signatures of your transactions, you're not putting them on blockchain. You just need to check them once, and then you throw them away. So if you use zero-knowledge proofs, we don't have to propagate them at all. Right. And yeah, there are a growing number of projects who are using zero-knowledge proofs for the applications. If you want to learn more about them, I highly recommend this awesome zero-knowledge proof list, where you will find introduction, you will find the list of tools, frameworks, presentations. Like, it's being constantly updated. If you have some ideas, if you're working on your project which uses zero-knowledge proofs, please do a pull request. We can update it and let everybody learn about your project. And this is it. Thank you very much. I'm happy to answer questions.
Hi there, great talk, thank you. On one of your slides, you gave some estimates on what a simple token transfer would look like. And it appears that most of the constraints come from the Merkleization. Does this mean that you could actually put, this would be the same estimate for computation for multiple transfers as well?
For what, sorry?
Does this mean that you could also do multiple transfers in this same proof, since a majority of the constraints come from the Merkle tree computation?
So to get the benefits of scaling with zero-knowledge proofs, you need to batch many transactions together. Because at least if you use it for layer 2, but also for layer 1, you want a big block of many transactions. You compute the proof of the entire block, and then you propagate to everybody just this one short proof for all of them. So what you see here is a cost of a single one of many transactions which will be included in this block. So if you have 1,000 transactions, you will have to pay this cost 1,000 times. So you will need 4,000 seconds of computational time on a similar machine, which of course you're not gonna use MacBook for this. What you're gonna do is you're gonna have a big cluster in some cloud, which will do this work all in parallel, so that your proofs are constructed quickly. But you will actually have to spend all this work for each of the transactions included in this block.
Can you use zero-knowledge proof to prove a certain computation for any Turing-complete computation?
For a Turing-complete
computation, like any computation, any arbitrary computation, can I use zero-knowledge proof to prove that I did that certain computation?
Yes, you can use zero-knowledge proofs to prove that you have done arbitrary computation. So you will have to deal with certain limitations. So I can give you a sense of what the limitations are, or maybe you want to formulate the questions more precisely.
Like, you can prove without doing that computation, right? Like the prover.
You have to do the computation. You have to actually do more work than just the computation itself. Order of magnitude more work.
Like, the prover needs to do the computation to prove it.
Of course, you need to do you need the computation, and you need all the inputs and all the intermediate values throughout the computation, throughout the execution trace of your computation. You cannot construct proofs for things which you would not be able to compute yourself.
Hey there, thanks. It was a great talk, really. We know with the ZK, basically, there are two major implementation options. We can store data on-chain or off-chain. And the trade-offs are obvious, and obviously, we can do a lot more if the data is off-chain. But then that introduces the data availability problem. I was just wondering, can you touch upon that? And maybe, I don't know, do you have any favorite approach? And just
absolutely. So if we put the data on-chain and we use it for scaling, then we have to define what does it mean to put data on-chain or off-chain. So we can use the chain to propagate the data, and then users can store it separately. What's really important is that we make the data available. So we solve the data availability on-chain. We don't need to use Ethereum storage. We can use just Ethereum call data to make it available to everybody who uses the application. Now, it depends on the kind of transactions which you execute. For transfers, a single transfer only requires 12 or 14 bytes of data to be propagated if we exclude the signatures. Now, this is very little. In terms of gas, it's something like 700 gas at the current price. From Istanbul, there is an EAP 2028, which reduces the gas cost for call data by a factor of 4 or 5, so it will be even less. And it's actually very cheap. But the benefits which you get from putting the data on-chain are enormous. You actually get the security properties of Ethereum. If you have to handle data availability off-chain, then you have to introduce either some complex games or data notaries which have to sign off the data, and so on and so on. And there are just too many security assumptions which users have to take. By putting them on-chain, you just completely eliminate the problem. And this is awesome. So I would argue that the current costs in case of transfers and similar operations are speaking in favor of putting data on-chain. If you have something which is very data intensive, then it's a different story, but we have to look at the exact use case. But what's important, zero-knowledge proofs just give you the ability to use the on-chain data availability because they compress the data. You just omit so many of data points which are redundant, which are not necessary to store, that it's actually possible. If we wanted to do data availability for Plasma on-chain, this would not be possible because you need to show all the signatures. So your data cost is 10 times more immediately. No, not 10 times, but maybe 7 or 8 times. It's still a lot.
Was a great talk. One question, can you elaborate a little bit on the smart contracts on private data, where you said it's in research?
It is in research. For smart contracts on private data, you need some kind of recursive composition of proofs if you want to use them. So of course, you can just have smart contracts where users produce the proofs that they perform certain operations and they publish them on-chain. But this is going to be pretty expensive. The cost of a single verification of such a smart contract is going to be expensive. Maybe it's OK for some use cases. If we want to be available in masses and be scalable, then we probably want something like users generate the proof of their own computation. And then we take all of these proofs and batch verify them together and produce a proof that we verified all of these proofs. And this is something what we in Matter Labs are looking at. This requires some changes in Ethereum if we want to use it on Ethereum. Namely, we need support for different elliptic curves, which will allow this recursive composition. Currently, Ethereum only supports BN256, which doesn't have nice embedding curves we can use. But BLS curves and MNT curves, they do have this. And this is why we sponsored the EAP 1962, which also has been included into Istanbul, but the second part of Istanbul, which is going to be released around January. And then we can use arbitrary elliptic curve operations on different curves, and then it will become possible. But this is a heavy research topic, which it will take some time to properly construct the languages and frameworks which allow you to easily manipulate this data. So some challenges around the logistics of data have to be solved and so on. But it's definitely coming. In a few years from now, it's definitely going to be here. Here?
So I just come in, maybe you have answered the question in the slides, but I'll ask it anyway. Do you think, because right now I'm not sure if it's totally practical to use ZKP for a lot of applications, so you think it's it's better to use it on chain or you use it in a side chain in the current stage. If I want to build applications to really use it for a lot of transactions.
If you want to use it for a lot of transactions, you need a side chain, because otherwise you would have to change the core of Layer 1 protocol, which is not happening anytime soon. But we're working on a Layer 2 sidechain solution where you can move funds from the main chain to the sidechain and then quickly transact in high volumes for very low predictable cost.
So you mean that you already have a sidechain ready for us to use it?
We have a sidechain. You can check our website, and there is
Okay,
a
cool.
link
Thanks.
to demo. You can see the demo actually on the mainnet running.
Thanks.
And thank you, everybody.